In this video I want to show you another representation of the Riemann zeta function, and in particular we know that zeta of s can be written as a sum over n from 1 to infinity, 1 over n to the power s, where s, the real part of s, is greater than 1. And I want to show you that in this case, for the real part of s greater than 1, this is also equal to 1 over the gamma function of s, integral from 0 to infinity x to the power s minus 1 divided by e to the x minus 1 dx, like this. And the proof is actually quite simple, and let me also remind you that gamma of s by definition is the integral from 0 to infinity x to the power s minus 1 e to the minus x dx. And then let's consider this denominator here, and in particular the function 1 over x e to the x minus 1. So I'm considering this function here, 1 over this, right? And this can be also rewritten as e to the minus x divided by 1 minus e to the minus x. And this is none other than the sum with the index n going from 1 to infinity of e to the minus x raised to the power n, like this. And now we can substitute this expression there in the integral, right? So we can rewrite this integral like this. So we have integral from 0 to infinity x to the power s minus 1 summation n from 1 to infinity, and then we have e to the minus x raised to the power n dx, like this, right? And now what I'm going to do is I'm going to make a substitution in the integral, and in particular first I'm going to put this summation outside the integral. So we have sum over n from 1 to infinity, and then I have the integral from 0 to infinity x to the power s minus 1, and then I have e to the minus x times n dx. And now I'm going to consider a change in the variable here. So we are going from nx to t. So this is the change of variable that I'm going to perform. X is equal to t over n. Okay, and therefore this will be equal to summation from 1 to infinity, and then we have integral from 0 to infinity t to the power s minus 1 divided by n to the power s minus 1. Then we get e to the minus t, and then we get dt over n. And now it's very easy to realize that basically here we get the summation over n from 1 to infinity of 1 over n to the power s, and then we have the integral there. But the integral, if you take a look at it, it is just equal to gamma of s, right? And when we divide by gamma of s, here we get exactly this formula. So this is another representation of the Riemann zeta function for, let me highlight that this is true if the real part of s is greater than 1. Okay, but now we are going to find an analytic continuation of this function, because if we used these formulas here, even for those cases which do not satisfy this condition, then of course we would get some divergences out of these expressions, right? It's very easy to realize that, because if, for example, s is equal to minus 3, then we get a summation of n cubed, but this will diverge by considering our common intuition, and it is indeed true that it diverges, but What we are trying to do here is we are trying to find another way to represent the Riemann zeta function for those cases that do not comply with this condition. And I will start discussing that from the next video.